In this video, we are going to learn about a new LLM framework called DSPy, which has been making quite a bit of buzz lately. DSPy is a Python library that allows you to do prompt programming with LLMs. I'll be showing you 8 examples, starting from DSPy's most basic building blocks to some more advanced and interesting examples, and end with a rather complex LLM system that just use those simple building blocks that we covered in this video. These examples will each introduce something special about DSPy, and I made these examples to be the simplest to understand and the most impactful as possible. So just follow along, and I hope that you will be ready to build your own LLM apps with DSPy by the end of this video. Welcome to Neural Breakdown. Let's go try DSPy. So it's important to understand why we should even learn about DSPy and prompt programming. And notice I said prompt programming and not the more common term prompt engineering. In prompt engineering, we write complex textual prompts to LLMs to make them complete a given task. This is an example of a prompt. Quite often, we will assign a role to the LLM, describe the task, maybe add some representative examples, and then tell it what output format we desire. In most LLM applications, we will also do prompt chaining, where multiple prompts are used sequentially to achieve some more complex multi-step task. And depending on the complexity of these chains, the task of writing the prompts themselves gets more and more hacky and cumbersome. Also, the prompts can return different outputs when the underlying LLMs themselves change, meaning overtuned prompts may get obsolete with the latest LLM release, introducing a maintenance overhead, inconsistent performance, and some technical debt to your application. And many experts claim that as the underlying LLMs get powerful and stronger, the need for excessive prompt engineering will slowly decrease. As developers, we shouldn't need to bother about writing these ultra-specific prompts or find the most optimal few short examples. We just want to learn general skill sets that can be applied to all types of domains and all types of language models. And with DSPy, we take a small step towards that direction, away from over-engineering individual prompts, but instead defining how the data flows through different modules within our LLM program. DSPy imagines every LLM application as a text transformation graph. Each node in this graph receives one or more text inputs, applies some text transformation, and then passes it on to the next node for further processing, until at the very end we receive our desired output. DSPy completely detaches the underlying model and the program that you designed, meaning you can teach both powerful models like ChatGPT or Mixtral and local, much smaller models like T5 or GPT-1 to perform the same task and use the same LLM program. Hope that's a good introduction for you to have some intuition about what problem we're trying to solve here with DSPy. Let's get started with the tutorial with example 1. Things are going to be even clearer from here. So the first example that we're going to look at is a simple example where we pass in a prompt to the LLM and we receive a response. We start off by importing DSPy, and then we create this OpenAI object, which basically wraps the OpenAI API calls within this DSPy object. And then we do some stuff to basically tell DSPy to use this particular language model object. And we say here that this LLM function is going to input a question and it's going to output an answer. Pretty straightforward, right? And the way we call this LLM after that is like we pass in a question like this. For example, I just passed who scored the final goal in the Football World Cup finals in 2014. And it basically returns us a prediction object. And if we see the answer of the prediction object, it's the right answer. And then if we do this turbo.inspect history, and again, this turbo is basically this OpenAI object, which is using this GPT 3.5 turbo model. And if you see this turbo.inspect history, it basically is going to return us the last prompt that was run by our LLM model. And you can see here, it starts the prompt by saying, given the field's question, produce the field's answer, which is basically a translation of this thing that we wrote down here. And then it says, follow the following format, and then it asks the question, and then this green part is what the answer is from the LLM. Although this shorthand formation is nice and cute, it is also limiting because we may want to define more description about our input and output. And for this, DSPy uses the concept of a signature. A signature is a specification of the input-output behavior in a DSPy module. Signatures allow you to tell the language model what it needs to do rather than specify how we should ask the language model to do it. And again, to define the signature, it's pretty straightforward. Here we have a class called QA, which is inheriting from DSPy.signature, and inside we mention the question as an input field and the answer as an output field. And then we again define this DSPy.predict class and we input the signature into it. And then if we run the same question again, we're going to get our answer back. And if you inspect the history, it's going to be the same prompt that we ran in the previous example. But if you use signatures, we can do more stuff than just that. For example, we can attach a description to each of our field. For the output field, I'm just saying the output should be between 1 and 5 words. And for the question, we are saying it's a user question. And we can also attach a docstring, which is going to be important. So if we run this, again, we're getting the same answer, but look at the prompt now. The stuff we put in the docstring is now the start, the beginning of the actual prompt that the LLM sees. And the question, instead of this kind of a Jinja template kind of a deal, we are now seeing user's question, and from the answer, we're seeing often between 1 and 5 words. So in the next example, we're going to talk about basic chain of thought. So in example 1, suppose we asked a more complicated question to the LLM. So for example, if you ask who provided the assist for the final goal in the Football World Cup finals in 2014. Now, obviously the answer is not Mario Götze, it's actually Andres Schürrle. But because we are just running this kind of a simple prompt where the LLM has to directly output the answer, it's failing at the job. One way to solve this is our example 2, which is to do a basic chain of thought. So in chain of thought, instead of just the old input, node, output, we basically ask the language model to think step by step in order to solve the problem. Let's see how that works in action. So to do chain of thought, instead of writing DSPy.predict, we will just write DSPy.chainofthought QA, where QA is obviously that old signature that we wrote in the previous example. And if we run this, then we will indeed see that the answer predicted by the LLM is the right one, Andres Schürrle. And if you look at the prompt now, it has added this additional reasoning step between the question and the answer. So it says reasoning, let's think step by step in order to produce the answer. And if you look at the LLM's generation, we know that the winning goal was scored by Mario Götze. The assist for that goal was provided by Andres Schürrle. And therefore, the answer is Andres Schürrle. And that's a part of chain of thought because you basically ask the LLM to output some thought before arriving at the answer. And often this makes the LLM reach down within its millions, billions, trillions of weights to extract some knowledge that it can't just extract on the fly. This is a good opportunity to introduce the term modules into our vocabulary. Just like signatures tell us what the LLM should input and output, modules define how it should do it. We have already seen 2 modules so far, the predict and the chain of thought, that both employ different algorithms to transform the input text to derive at the answer. And we can even define custom modules on our own very simply. Say we have this kind of a multi-step question which says, what is the capital of the birth state of the person who provided the assist in the Football World Cup finals? So if we let our chain of thought module answer this, then the rationale that it produces is, it says, we first need to identify the person who provided the assist, and then we need to determine the birth state of that person. And then it just randomly says Munich. Now, Munich is not the right answer. But what if we wrote a custom module for this? Here in the init function, it basically creates that same chain of thought object, and inside the forward function, it just calls that chain of thought object and passes in the question. And then again, if we input that multi-step question, we again get back Munich, obviously, because we haven't really done anything special here. But because we have it set up like this, we can now add more stuff inside this module. So here I've written a class called double chain of thought, where basically we have 2 chain of thoughts. The first one inputs a question and outputs a step-by-step thought. And the next one inputs a question and a thought, and then outputs a one-word answer. Now, obviously, you can write signatures for this, but for simplicity, I've just gone with the simple shorthand notation. And inside the forward function, it first called the first COT1 object, where we just pass in the question, and then we take the step-by-step thought that it generates to pass it to the COT2 object, where we pass in the original question as well as the thought returned by the first COT1 object. And if we run this, it turns out that we get a different answer. The player who provided the assist for Mario Goetze was Andre Schurl. Andre Schurl was born in the state of this. Therefore, the capital of that is Mainz. And if we did inspect history, and let's say we take the last two, and then we will see that the first prompt it runs is it takes a question and outputs this step-by-step thought, where it basically discovers that the person we need to find more about is this guy called Andre Schurl. And in the second one, it basically takes the thought and then determines the correct answer. And that is the power of being able to stack multiple smaller modules inside your much larger LLM program. The whole concept of a module is inspired by deep learning frameworks like PyTorch. Just like PyTorch, we define how the data graph would look like, and inside the forward function, we shall define the logic which transforms the input to get us our output. In fact, in the documentation, they say that DSPy is the PyTorch for foundation models. So in example 3, we are looking at outputting typed predictors. So far, we have only been able to output strings from the LLM. But what if we want to output a float or a boolean or something? The way DSPy suggests we do this is via the library Pydantic. So for example, maybe instead of just the answer, we also want the LLM to output the confidence about how much the LLM is sure about its answer. To do that, we define this Pydantic base model object where we define our output. The answer is a string and the confidence is a float, which is between 0 and 1. And inside our signature, we, as usual, mention the input field, but for the output field, we refer to the base model object we created up here. And then we define our prediction object, but instead of just DSPy.chain of thought, we use typed chain of thought. And then if we ran that, the confidence output that it returns is indeed 0.9 and its type is float. And if you look at the history of how this was generated, you are going to see that it basically enters the JSON schema in which the output should be formatted. So it says that you must use this format, and it also produces this JSON schema from our Pydantic class structure. And that allows the model to generate the JSON in the right format. And now let's look at a little more complex predictor, maybe like a JSON. We want the LLM to generate a list of the country and the year of FIFA World Cup winners from 2002 to present. As usual, we write our base model, which is going to contain the country and the year. Inside the DSPy.signature, for the answer, we're actually going to mention a list of these objects. And then once again, we call our question. And here we get the answer in the right format as we were hoping for. Do keep in mind that this type predictor stuff isn't guaranteed to always work, because it might happen that the JSON that the LLM returns is still incorrect, because we are not really doing anything to force the LLM to output in a particular schema. We're just kind of, asking it to do it, just kind of, nudging it, saying, please, you must follow this format. And the LLM is obliging by following the format. It doesn't explicitly have to. So quite often we would want to do an LLM call where we would pass in external information that might not be readily available to the LLM. This is called retrieval augmented generation. Given an input prompt, the LLM defines a query. We take this query and search a database. The database returns us some passages or some information. And finally, we then call another LLM module with this newly added context and ask it to generate the answer to our original question. So let's see how the RAG framework can work in DSPy. As usual, we import DSPy, we create our GPT Turbo model, and we also initialize this DSPy.colbert v2 object. So this Colbert v2 is basically a retrieval server where they have the abstracts of many Wikipedia articles till the year 2017, and it is available to use for free. You can use other databases as well, like Milvus or ChromaDB or other local databases, but since Colbert v2 is free to use and already comes with a lot of data, we are just going to stick to this. So to use this Colbert v2 retrieval model, we basically have another DSPy module called DSPy.retrieve, and here we're saying retrieve the 3 most relevant passages for the query string under Shirl. We see that the top k passages are these ones, and the first one is actually about the German professional footballer who we are looking for. And obviously if I change it to something, I don't know, like iPhone, it is also going to update it with entries about the iPhone. Now how can we use this information to create an LLM app? Let's say we're asking the question, what is the date of birth of the player who provided the assist? And obviously if you ask this question with a normal chain of thought, it doesn't give the right answer. But here we can see this information is actually present in our retrieval database. So is there a way that we could retrieve these passages and extract the date of birth from here? To do that, we can create this RAG module. The RAG module has just 2 things, the retrieve and the chain of thought. And if you look at the signature used by the chain of thought, it basically inputs the context and the question and outputs the answer. The context obviously comes from the top passages from the retrieval algorithm. And in the forward function, we pass in the question into the retrieve, and then whatever it generates, we basically use it to predict the answer. Turns out that doing it like this doesn't work. This is a wrong date of birth. If we can look at the turbo.inspect history, we can see that under Shirl passage that we wanted this model to retrieve, it has not actually retrieved. And the reason why is that the input to self.retrieve is the question itself, but ideally we want it to be under Shirl and not the question. So in example 5, we are going to look at a different algorithm to get this done. By the way, if you're enjoying this video, the best way to support the channel is to just hit the like button, drop a comment, and subscribe to the channel, because if you like this video, you're probably going to love my next one. We also have a Patreon where I post channel updates as well as the slides, write-ups, animations, code from all of my videos. A huge thanks to all of our supporters this month across Patreon and on YouTube. Your support means a lot. Thank you. Let's get back to the video. So the LLM program that we are instead going to try to do is called multi-hop reasoning. If this is a RAG, multi-hop reasoning adds a loop inside the RAG. After we receive a question, we're going to ask the LLM to output a query, and then we're going to query this to our database. The database will return us some passages which we're going to include in the prompt next time to again output a different query, and then again ask for more information from the database. We are basically going to run this in a loop until we get our answer. And let's see how this is implemented in DSPy. First off, we do our setup stuff, and then we have the generate query signature. The generate query signature takes in the context and the question, and it outputs a query. Of course, the generate answer stuff is the same as it was before. And then we write our multi-hop module. The multi-hop module takes as input the passages per hop, which is going to be used for our retrieval, and the max hops, which is the max number of times our program is going to try to loop to find the correct answer. The init function a little more closely, we got this list of chain of thoughts where the signature is this generate query stuff, which takes the context and the question and outputs a query. And here in the forward function, we loop over our self.maxHops. We generate a query given the current context and the question. We extract that query. We find the passages that are inside those queries. We run a deduplication step so that we don't have duplicate queries inside our context. And finally, after this thing has run for 3 times, we generate the answer. And if we ran our question through this one, we indeed see that we get to the correct answer, 6 November 1990. And if we look at the contexts that it retrieved that entry about the 2014 World Cup final, and it also outputted the Andre Shirley passage as well. And if you look at the inspect history, you're going to see the queries that the model was looking for. So the first one was data of the birth player who provided assist for the final goal, and that returned a context about the World Cup final. And here, using chain of thought, it determines that the person who provided the assist was indeed Andre Schurrle, and we need to find his date of birth. So it searched for date of birth of Andre Schurrle, and this is when it retrieved the Andre Schurrle passage, where it was able to determine what the answer is. And next, we are going to look at a classification problem and how we can use few-shot prompting to improve LLM accuracies. So going with the theme of today's example so far, we have a data set here that describes a situation in football and what the referee decision should be. I basically generated this data set with Claude, and I'm going to see if GPT is able to do well on it. So at first, we are going to create these dataset objects, which is basically going to be a list of DSPy.example. Those examples just contain the question and the answer within them. And then we are going to create our signature, which is going to have the event and the answer. And we're going to create a basic predict model that just contains a chain of thought. And then if we ran this evaluate function, which takes in a test set, which is just a list of these DSPy examples, and a metric, and in this case I'm using the answer exact match metric, which is going to return 1 if the predictions and the ground truth are the same, and otherwise it will return 0. And if we run this evaluate program on this predict model thing, you're basically going to see the accuracy is like 37.1%. This is called zero-shot classification, since the LLM does not receive any hint about the expected input-output pairs. But if we begin to add some examples into the prompt, we will soon see that the LLM's performance go up, and this is called few-shot prompting. So the plan is we have this huge data set, and we are simply going to add some of these examples into the prompt and hope that our model does better. But the question is still, how do we determine which examples to pass in? We sure can't pass all of the 100 examples. Maybe we only want to pass 10 examples, but how do we decide which 10? Normally, if you're doing prompt engineering, we will handpick 10 examples that we think will work well and call it a day. But with DSPy, we can run experiments where DSPy will bootstrap different combinations of the prompts and test the LLM's accuracy and optimize for the best combination of examples to show to the model to increase the overall accuracy. And what if we try to bootstrap using DSPy's built-in teleprompt module? So this teleprompt thing is basically like an optimizer, and we use this bootstrap few-shot optimizer which inputs some of the examples from our train set into the query and then sees if that improves the prediction. And this bootstrap few-shot is an optimizer that takes a program, the training set, and a metric, and returns a new optimized programs. And for bootstrap few-shot, we pass in our train set, which is again a list of examples that the bootstrap few-shot algorithm must choose from to insert into our prompt. And we run this compile function, and then it takes like 3 minutes to run, and it returns us a new predictor or a new object which is optimized for the current task. And again, if we run this evaluate on the test set, we see that it has now gotten 36 out of 62 right, which is an accuracy about 58.1%, which is higher than the 37.1% it was receiving earlier. This is also a good opportunity to talk about DSPy's Assert and Suggest framework. Whenever we want to add constraints to our LLM's output, we would use Assert or Suggest. For example, in this case, we want the model's output to always be one of the following categories. So we can add a suggest statement to nudge the LLM to predict within these 6 categories if it outputted something else. So every time the LLM outputs something that's not one of these 6 categories, we're going to throw a custom error message as well as its previous output and ask the LLM to output the right thing. The main difference between suggest and assert is that after some retries, if our condition is still failing, we would basically halt the program right there if you're using assert, and if you're using suggest, we will let the program flow to the next step. Assert literally stops the program on its tracks, and suggest just nudges the LLM to output the right thing, and if it doesn't do, it just continues the rest of the downstream tasks anyway. And so to do suggest, we just basically add this additional line inside our predict model function where we just say the output answer should be in the following list, and in case it is not, then it's going to throw this error message to the LLM. And then let's see the difference when we run it without the suggest. So without the suggest, the output is offside, which is not part of our 6 categories. But if we run it with predict model assert, we see the answer is VAR, which is indeed present in our category list. And if you look at the inspect history of this, we do see that originally the model did predict offside, but then we informed it that the past answer was offside, and the instruction is the answer can be only one of the following, and then yellow card, red card, etc. And this results in a change in the output to VAR. Okay, so it's time for example 7. In example 7, our goal is to generate a new question answering dataset. But there's a caveat. We only want to generate question answer quizzes from the information that we have access to in our Colbert 2 database. So how this algorithm is going to go is that we are going to generate a random list of search terms, and we are going to query our Colbert 2 database using these queries, and the passages that we receive, we're going to ask an LLM to generate quizzes out of those passages only. So all the questions in the quiz can be answered by looking at the database, and no external knowledge is required. And let's see how we're going to build this. So I have the list of search terms right here, and for our signature, it's a pretty simple one. Our doc string says that generate a very simple trivia question from the given information. The information is going to come from the retrievals, obviously, and then as output we have the question and the answer. And here in the forward function, we input the query, which will come from this list. We're gonna pass that query into our retrieval module to get back those passages relevant to the query, and then we're gonna loop over each of those passages, and we're gonna call our chain of thought module to output a question and an answer from those options. And we're going to keep a list that appends all of the context, questions and answer. And then if we run that whole thing, we're going to end up with a database with questions and answer, and also the context which we retrieve from the database from which the question was generated. So a lot of times we would want to train a much smaller model on a task that has already been learned by a much larger LLM, where we take a large model and transfer its knowledge to a much smaller model. And that's what we're going to do now. And for our final example, we want to train a T5 model to A, learn how to query the database given a question, and B, given the passages returned by the database, learn how to generate the correct output. Let's see how we're going to do that. So first off, we have our trivia.csv, which we generated in the previous file. Of course, it has a lot of these question answer pairs, but we don't know how to generate the query that must be sent to the database to retrieve the relevant passages used to produce these answers. And for that reason, we are not going to directly train T5 on this input output pairs, but instead we're going to first build a RAG pipeline using GPT, and then use that to train our T5 model. And that way the T5 model is not going to learn how to generate answers from questions, but it's going to learn how to generate queries from questions and answers from the passages returned by the database. Let's see that in action. Here we have a generate search query signature whose task is to input a question and write a simple search query. And we have the generate answer signature that will take a context and a question and output an answer. And the RAG module inputs a question, it generates a query based on the question. The retrieval client returns some informative passages, and we pass that in as well as the question itself into the generate answer. And then we use that answer to compare with the ground truth answer. Let's see how the normal GPT 3.5 does on the quiz. To no one's surprise, it does pretty well, having a score of 83.3% by getting 25 of the 30 questions on the test set. Given the question, it is able to find the right query to input to our database, and then given the context that's generated by the database, it's able to generate the correct answers. Now, how can we transfer this behavior to a much smaller T5 model? But before fine-tuning, let's see how much a T5 model actually scores. It actually scores 0%, and the reason why is because it's not able to generate the queries correctly, and obviously because the queries aren't right, the retrieved context is not right, and it's not able to generate the answer correctly either. So now let's take the RAG that's run by GPT 3.5 Turbo and then use that to fine tune our T5 small model. Now notice that GPT 3.5 has 175 billion parameters, whereas T5 small just has 60 million. But let's see how the fine tuning goes. To fine-tune, we will use DSPy.teleprompt's bootstrap fine-tune class. We will create our training data, initialize the GPT RAG module, and then finally, when doing the fine-tuning, we will use a T5 small as our target. Here, the teacher model is the GPT_RAG, which is basically the RAG model controlled by GPT 3.5 Turbo, and the student model is controlled by T5 small, and then it takes about 6-7 minutes to run the 10 epochs, and as you can see, the evaluation loss is indeed going down as the epochs are progressing. And at the end of the epochs, we get back this RAG T5 fine-tuned, which is basically an optimized model that has learned from the teacher GPT 3.5. Let's see if this fine-tuned model can output some sensible answers. Here I've passed in the question, home of which football club is Emirates Stadium, and the query that the T5 model generated is Emirates Stadium. And if you see the retrieved context, it is actually retrieving a passage about Emirates Stadium where it does say that it is the home of Arsenal Football Club, and that helps the second part of our pipeline to generate an answer saying Arsenal Football Club. To remind you how our RAG pipeline worked, it basically had these two modules. The first one generates a query, and then the second one generates an answer from the context retrieved by the query. And here are a couple of more examples. Like for this one, we are asking him where the UEFA Euro 2008 took place, and it is correctly retrieving the right context to output Austria and Switzerland. In fact, if we ran our evaluation function on the new T5 fine-tune model, the performance is actually pretty good. It gets 50% of the answers correctly, scoring 15 out of 30. And that is much higher than the 0 it was doing earlier. And here are some of the correct answers that this T5 model was able to find out, and that's quite encouraging. Now obviously the original GPT 3.5 Turbo model scored an 83%, and we are still not there with just a 50% accuracy. So here I fine-tuned, again following the same algorithm, I fine-tuned T5 base, which has 220 million parameters, about 4 times as larger as T5 small, but still a lot smaller than GPT 3.5. And if we ran the training again, you'll see that the evaluation loss is indeed 0.07. The evaluation loss for the T5 small model ended in 0.15 after the 10 epochs, meaning that the larger model is definitely able to extract answers much better. And indeed, if we run evaluate, we'll see that it gets 21 out of 30 right, meaning a 70% accuracy. And here are some of the queries and some of the answers that the T5 base model was able to generate. And that's quite encouraging because we have succeeded in fine-tuning a model that is 1000 times smaller than the original GPT 3.5 model and still managed to achieve a solid performance boost with only 5 to 6 lines of code and just 5 to 6 minutes of training. So that is the end of this DSPy tutorial. We started with the basics of DSPy like signatures, then we talked about modules and all the different types of modules like predict and chain of thought, and how to write your own modules and your own text transformation graphs. And then we talked a little bit about things like RAG and retrieving from an external database and multi-hop reasoning. We talked about type predictors and DSPy assertions, and also how to do few-shot prompting and optimize our few-shot prompts. And finally, we talked about fine-tuning, where we took a compiled LLM program and then transferred that knowledge into a small local T5 model with pretty decent accuracy. I genuinely think that these DSPy guys are onto something. It's a really cool idea to create LLM programs that are just about the flow of data, and I think it's a great idea to decouple the programming portion of it from the modules portion of it. But let me know in the comments if you had any questions and if you are building anything with DSPy. If you enjoyed this video, please do hit the like button and share it with your friends. I'll see you next time. Bye.